Let us see rectangular waveguides and the propagation of TE modes in the rectangular waveguides and analyze the rectangular waveguides for the TE mode analysis. So, myself Dr. V. Vijay, Associate Professor, Department of ECE. Let us see what is the outcome of this session. At the end of this session, the student will be able to analyze different TE modes propagating through the rectangular waveguides. So, we obtain the TE wave equation and we also obtain the field expressions and we see what are the TE modes that are propagating through the rectangular waveguide. Let us see TE wave equations. To obtain the TE wave equation, as we have seen in the previous sessions, we have discussed about the Maxwell's equations in the previous sessions. So, now let us see directly that what is a transverse electric wave, and from the Maxwell's equation we obtain the Helmholtz wave equations and we apply this Helmholtz wave equation in the Cartesian coordinate system and derive the TE wave equation. See, transverse electric wave. What is a transverse electric wave? We have already seen this. Transverse electric wave means where the electric field is perpendicular to the propagation, and so here this Ez is equal to 0 and only the Hz component exists. Hz is not equal to 0. So, this equation previously we have discussed about the Helmholtz wave equation and what is the TE wave equation and TM wave equation, and so TE wave equation is represented by equation 3 and where that equation can represent it using del square over the Cartesian coordinate system, and Cartesian coordinate system means it is a rectangular coordinate system having the coordinates x, y, z. So, we are expressing this del square in terms of x, y, z. Okay. So, our equation is nothing but TE wave equation is nothing but it is del square Ez is equal to minus omega square mu epsilon Hz. Okay. So, this is our TE wave equation which represents in equation 3. For reference, I have written here as del square Ez is equal to minus omega square mu epsilon Hz. So, here in this equation we expand this del square in the Cartesian coordinate system as with respect to x, with respect to y and with respect to z, right. So, here this is Hz, this is equation 3, and so now we have expressed this dou square Hz by dou x square plus dou square Hz by dou y square plus dou square Hz by dou z square is equal to minus omega square mu epsilon Hz. So, let us consider it as equation 31, and as we have seen in the TM, here also we take dou by dou z is a propagation constant, dou by dou z is equal to minus gamma, and hence dou square by dou z square you can write it as it is with a operator that is gamma square, okay, with the operator gamma square. Okay. So, let us substitute dou square by dou z square here with this gamma square. So, dou square by dou square Hz by dou x square plus dou square Hz by dou y square plus gamma square Hz is equal to minus omega square mu epsilon Hz. So, here now if you substitute this, if you bring this minus omega square mu epsilon Hz to this side, you will get gamma square plus omega square mu epsilon Hz is equal to 0, and we consider this gamma square plus omega square mu epsilon as a constant. So, we can consider it as equal to h square. So, dou square hz by dou x square plus dou square hz by dou y square plus h square hz is equal to 0. So, this is completely a second order differential equation in terms of x, y, and this term, the third term h square hz is completely a constant. So, now we can expect a solution for this second order differential equation, and so the solution for this equation, the solution for this equation can be assumed to be hz is equal to some x y, hz is equal to some x y, where x is pure function of x only and y is pure function of y only. So, that means x is a function of x, y is a function of y, where x is function of x and y is, say, function of y. So, pure function of x and y. So, if we take this hz is equal to xy and let us substitute this xy in equation 33. So, we are going to get the equation dou square xy by dou x square plus dou square xy by dou y square plus h square xy is equal to 0. Now, as we are going to differentiate here with respect to x, and this is a partial differentiation, y becomes a constant, and as we are differentiating here with respect to y and it is a partial differentiation, x remains constant here, and here both h square xy, both x and y are variables, and so we are going to get the equation y dou square x by dou x square plus x dou square y by dou y square plus h square xy is equal to 0. Now, divide this entire equation with respect to xy, because here y is out and here x is constant. So, let us as it is a combination of both x and y, still if you divide this entire expression with xy, this third term becomes pure constant and the first term becomes pure function of x, second term becomes pure function of y. See, if you divide this equation with xy, see what happens. This is y dou square x by dou x square by xy plus x by xy dou square y by dou y square plus h square xy by xy is equal to 0. Now, this becomes, y gets cancelled and this becomes 1 by x dou square x by dou x square plus 1 by y dou square y by dou y square plus h square is equal to 0. Now, in this equation, this term is a term which is having only x, and the second term is having a function of y, and the third term is remaining to be constant. So, we can consider this equation as 36, and now we can expect the solution for the first term and second term, because this is a simple second order differential equation which is having a term of x term and y term. So this term completely have a solution in terms of x, and this term completely have a solution in terms of y. Already we have expected the solution, that is 1 by x dou square x by dou x square as some b minus b square, and 1 by y dou square y by dou y square as minus h square a square in the while deriving the TM wave equation. We will see once again. Let us consider this 1 by x dou square x by dou x square is equal to minus b square, and 1 by y dou square y by dou y square is equal to minus a square. Then this equation becomes in the form of h square minus a square minus b square is equal to 0, or we write it as h square is equal to a square plus b square. So if you observe this equation, h square is equal to a square plus b square, same like in TM wave equation we got the h square is equal to a square plus b square, where a is again say 1 by y dou square y by dou y square is equal to minus a square, and 1 by x dou square x by dou x square is equal to minus b square. And this equation 36 is exactly representing the same equation what we have seen in the TM wave equation. So the solution for this equation will also be exactly same as we have discussed in the TM wave equation. So for this equation h square is equal to a square plus b square, the solution is that as we are deriving for hz, so that means we can obtain what is x and what is y. So that is x we can write it as equal to c1 cos bx plus c2 sin bx, and y we can write it as c2 cos ay plus c3 sin ay. So let us see what is x. X is equal to c1 cos bx plus c2 sin bx, and y is equal to c3 cos ay plus c4 sin ay. So we have derived what is x and what is y using these equations. 1 by x d square x by dou square x by dou x square is equal to minus b square, and 1 by y dou square y by dou y square is equal to minus a square. So as we got this x and y, now we can substitute this x and y in hz is equal to xy. So we can get the equation for hz. We can get the equation for hz. Can get the equation for hz, where hz is equal to c1 cos bx plus c2 sin bx into c3 cos ay plus c4 sin ay. So let us use this, let us consider this TE wave equation and obtain the boundary conditions in the rectangular coordinate system. So what is the boundary conditions and how we are going to express these boundary conditions in the rectangular coordinate system? Same like we have seen in the TM wave. See, we are considering the broader dimension of the rectangular waveguide on the x-axis and the smaller dimension of the rectangular waveguide on the y-axis. So the broader dimension of the rectangular waveguide is A, and the smaller direction on the rectangular waveguide is B, and so actually this is the z axis, and so this is the negative z direction, that is the direction of propagation. So this is a hollow rectangular waveguide, and hence the wave is propagating in the rectangular waveguide, and this rectangular waveguide is having boundaries. So let us see what are the different boundaries we are having. So there are different boundaries. First let us see the bottom wall. So this is the bottom wall. So bottom wall is on the bottom side, that means here this is the x dimension, so we can consider this is 0 0 origin, and here x is changing a, but y still remains to be 0, so we can write it as a comma 0, and this is the position where y is changing from 0 to b, but x still remains to be 0, it is 0 comma b, and this point coordinate we can call it as a comma b, right. So on the bottom wall, as we have x is changing from 0 to a, y remains to be 0, that is our condition. Y is equal to 0 for all x changes from 0 to a, and here in this, while deriving the T wave equation, we take the field expression Ex is equal to 0, because here x is a continuous variable, we take the field Ex is equal to 0. Remember, wherever the field is continuous, here if y is continuous, Ey is equal to 0, if x is continuous, we take Ex is equal to 0. Now let us take the another boundary condition, another boundary, that is left hand wall, left wall. So left side wall means this is the left side surface, and on this left side surface the y is changing from 0 to b, where x remains to be 0. So the condition is x is equal to 0 for all y changes from 0 to b, okay. And so as y is a continuous variable, here we equate Ey is equal to 0. And similarly, remember one thing, only the electric field component can become 0, but not the magnetic field. So we don't make Hx or Hy to be 0, we take only Ex and Ey is equal to 0. Then let us consider the top side surface. So this is the top surface, and on this top surface, here y remains to be constant b, but x is a continuous variable changing from 0 to a. So x is changing from 0 to a and y remains to be constant b, and so as x is a continuous variable, we make Ex is equal to 0. And then we go for the right hand side surface wall, and let us consider this purple color for right hand side surface wall. And so this is going to show that on this wall x is constant a, and y is changing continuously from 0 to b. So hence Ey is equal to 0. So these are the 4 boundary conditions we are having, that we need to substitute these boundary conditions on the TE wave equation. So let us see what is the TE wave equation. Once we write what is the TE wave equation, we got Hz is equal to C1 cos Bx plus C2 sin Bx into C3 cos Ay plus C4 sin Ay. Now let us see, applying the boundary conditions one by one, let us derive these arbitrary constants. We will reduce these arbitrary constants. See, for example, now if we consider the first boundary condition, the first boundary condition is going to say that Ex is equal to 0 for all x is changing from 0 to a, where y is equal to 0, where y is equal to 0. Now substitute, we need to find what is Ex. Already we have derived the field expressions while discussing the TM wave equation. So we write what is Ex. Ex already we have it as minus gamma by h square dou Ez by dou x minus j omega mu by h square dou hz by dou y. And here in our T wave equation, hz is some c1 cos bx plus c2 sin bx into c3 cos ay plus c4 sin ay. This is our equation 37. And as it is a T wave equation, we know z is equal to 0. So let us substitute z is equal to 0 and hz here. So as z is equal to 0, the first term will vanish and you are going to get minus j omega mu by h square into dou hz by dou y. So we have to apply the differentiation with respect to y. While applying the differentiation with respect to y, the x term remains constant. So we take the x also as a constant, that is c1 cos bx plus c2 sin bx is a constant, and then differentiation with respect to y, that is as y is equal to 0, as y is equal to 0, differentiation with respect to y at y is equal to 0. So at y is equal to 0, this term becomes cos a 0, that is simply 1. So this is c3, it is a constant. So c3 plus c4 sin 0 becomes 0. So this entire has become 0. So we will get it as, first we differentiate, that is c3 into differentiation of cos function, it is minus a sin ay plus c4 into differentiation of sine function, that is c4 a cos ay. Okay. So we have two terms, c3 minus a sin ay plus c4 a cos ay. So a is also the constant comes out, and so we can write it as minus j omega mu by h square into a c1 cos bx plus c2 sin bx, and this term becomes c4 cos ay minus c3 sin ay. This is Ex, and of course we equate this field expression to 0 for all y is equal to 0 and x is changing from 0 to a. That means y 0 we need to substitute here. If we substitute this y is equal to 0, this function becomes cos 0 whose value is 1, and this function becomes sin 0 whose value is 0. Okay. So let us substitute that sin value as 0 and cos value as 1. So we are going to get Ex. See what is Ex? Ex is equal to minus j omega mu by h square A C1 cos bx plus C2 sin bx and into see when y is 0 cos ay becomes 1 and sin ay becomes 0. So, this term finally this term will vanish and you are having only C4 here and into C4 is equal to 0 is equal to 0. See here in this Ex is equal to 0 we have either j omega mu by h square to be 0 or A need to be 0 or this term need to be 0 or C4 should be equal to 0. So, in all these cases this term is not equal to 0 because x is continuous variable. So, C1 cos bx plus C2 sin bx is not 0 and if A has become 0 obviously the entire cos C1 function will become 0 and so j omega mu by h square is also not equal to 0. Obviously C4 should be equal to 0. So, this is our C4 which is equal to 0. Let us substitute this C4 in equation 37, that is Hz is equal to C1 cos Bx plus C2 sin Bx into C3 cos Ay plus C4 sin Ay, but C4 is equal to 0. So, this term will